So imagine navigating your daily commute by steering your car using the check engine light instead of the actual steering wheel.
I mean, you'd crash before you even made it out of the driveway.
It sounds completely ridiculous.
Yeah.
You'd be taking a diagnostic tool,
Right.
something that it's literally just designed to tell you what's going on under the hood, and you're trying to use it to perform the actual mechanical action of driving.
Yeah, and that light has zero mechanical connection to the wheels. It's just an indicator.
Exactly. But the crazy thing is, in the world of software engineering, we see highly paid developers doing the digital equivalent of this all the time.
Oh, constantly. Yeah. They use these diagnostic outputs to drive the core logic of their applications.
And that is exactly what we are getting into today. Welcome to today's deep dive. If you've ever wondered why a banking app suddenly crashes, or, why a seemingly minor update to a website breaks a completely unrelated feature, you are in the right place.
It's a hugely important topic.
It really is. Today, we are looking at a developer journal entry from June 10th, 2026. It's written by a programmer named Ang, and the post is titled, Notes on Haskell Programming Part 158, Moving Away from String Manipulation.
And look, I want to say right up front, even if you have zero technical expertise, like if you don't write Haskell, if you don't deal with code at all, you really need to stick around for this one.
Yeah, because this isn't really about the code itself, right?
Exactly.
Yeah.
The core mission here is not about memorizing syntax. It's about understanding this massive paradigm shift from building really fragile, tangled systems to creating robust, specialized ones.
Right.
Ang takes us through this process of basically abandoning a brittle, string-based approach for what they call an elegant, type-safe, and idiomatic design.
Which sounds very technical, but it's really a universal concept.
It is,
Yeah.
because that philosophy applies whether you are architecting a massive software platform or, organizing a corporate department or even just structuring your own personal files.
Right. It's about how to not build things that break easily. So to really appreciate the beauty of the solution Ang eventually lands on, I think we first have to look at the original code.
Yeah, let's look at the crime scene.
The crime scene, exactly.
Yeah.
So the developer was experiencing a lot of anxiety over this piece of logic that, honestly, it sounds incredibly simple on the surface. It's just saving an exported file with the correct file extension.
Right, which is a foundational task for any software that handles files.
Right. So if you, the user, export a document, the system just needs to name it and slap a .pdf or a .text at the end of it.
Super basic.
Right. So in Ang's system, there was a specific function tasked with doing this, and it was called getOutputPath.
Okay.
And it required two pieces of information to do its job. First, the file path, which is just the destination folder, and second, an export format, which is represented in the code by a variable called FMT.
So it knows where the file is going, and it knows what format it's supposed to be in.
Exactly. It has the destination, it has the format.
Yeah.
But here is where the logic takes a very strange turn. Because to figure out the actual letters that make up the file extension, the original code relied on this maneuver called string manipulation.
Oh, boy.
Yeah. It took that format variable, the FMT one, and it ran it through a debugging function called show.
Okay, so let's unpack that, because show is a very specific tool in Haskell.
Right.
It basically takes a piece of internal data and it converts it into a human-readable string of text. So if the internal format is PDF, the show function spits out the text string PDF, and usually with a capital P.
Okay, but the code didn't stop there.
Right.
It took that output text, that capital PDF, and pushed it through another command called map to lower, which basically forces every single letter to be lowercase.
Right, squishing it all down.
Yeah, so now it's lowercase PDF. And then finally, it handed that lowercase text over to a final command called replace extension, which glued it onto the end of the file path.
So the entire file-saving mechanism was hinging on capturing text meant for a debugging log. Right. Scrubbing its capitalization and then blindly pasting it onto a file name.
Exactly. And, I have to admit, when I first read this in the source material, I actually thought it sounded kind of clever.
Really?
But yeah, think about it. If the system already knows the format internally, why would you write out a whole redundant list of file extensions? Asking the system to just print its internal name and making it lowercase, it seems like a highly efficient shortcut.
I see why it's tempting. It feels like a neat trick.
Right. So what's the actual harm in doing it this way? I mean, going back to our analogy, if using the check engine light gets the car down the road, why is it bad? Is this why developers call code brittle?
That is exactly why they call it brittle. And the harm really lies in the fundamental difference between a type and a string and what a compiler can actually protect you from.
Okay, break that down for me.
So when you write code, the compiler acts like a rigorous inspector. If you try to, say, multiply a number by a color, the compiler stops you before the program even runs.
It's like, no, you can't do that.
Yeah. Right. It says, these types don't match. I won't allow this. And that is what we call a compile time guarantee.
So the factory tests the engine before the car ever hits the road.
Precisely. It catches the error in the factory. But a string, which is really just a sequence of text characters, is essentially invisible to that inspector.
Invisible how?
Well, to the compiler, the string PDF is mathematically no different than the string banana or, a string of random emojis.
Oh, wow. Oh, well.
So when you rely on string manipulation to drive your core logic, you basically strip away all of the compiler's safety checks. You are actively pushing the risk from compile time, where it's caught safely in the factory, to runtime, where the user is actively driving the car on the highway.
So you're just flying blind.
Completely blind.
The system is just randomly gluing letters together and hoping the operating system actually accepts it as a valid file extension.
Yeah, and worse than that, you are actively misusing the tools you have. Eng points out in the journal that the show instance generating this text is, quote, typically reserved for debugging. When developers look at a massive wall of logging data to figure out why a server crashed at, 3 a.m., they rely on show to give them a human-readable readout of the system's state.
It's just for human eyes.
Exactly. It is a diagnostic tool. It is absolutely not meant to be a load-bearing pillar for your actual file system logic.
Wow. So this really does go right back to the check engine light analogy. The code was using an indicator light to physically shift the gears.
Yes, and that introduces what is arguably the most dangerous concept in all of software architecture, which is tight coupling.
Tight coupling.
Yeah. When two completely unrelated parts of a system become invisibly dependent on each other, you have built a trapdoor.
Okay, so Ang actually explores this exact trapdoor in the notes.
Yeah.
To understand how tightly coupled this was, we really need to look at the specific data type that Ang was working with.
Right, the export format type.
Yeah, exactly, export format. The source material lists out the specific formats the system handles, and it's PDF, type, EPUB, TXT, and MD, which is for Markdown.
Right. And crucially, Ang notes that this export format data type, quote-unquote, derives a few standard type classes automatically.
Okay, what does that mean?
Well, specifically, it derives show, EQ, enum, and bounded.
And the show one is the troublemaker here.
Exactly. By deriving show, the system automatically generates that readable text for the debugging logs. So the internal format PDF automatically turns into the text string, capital PDF, when the debugger asks for it.
And because the file-saving code was eavesdropping on that exact output, the logging system and the file system were basically handcuffed together.
Yes, permanently handcuffed.
Okay, here's where it gets really interesting to me. Let's play this out. If I understand this right, let's say I'm a new developer joining this team, 6 months later.
Okay.
I wouldn't necessarily know about that invisible handcuff, right?
Not at all.
So let's say I'm assigned to improve the logging infrastructure because, I don't know, the operations team is complaining that the server logs are too cryptic to read.
Sure, happens all the time.
Right. So I look at it and I see the output just says PDF and KIP. And I think, oh, I'll be helpful. I'll make this more descriptive. I change the show output so it prints PDF document in TIPS format instead.
Which is a completely innocent, highly responsible change. You are making the diagnostic tools better for your team.
But the moment I deploy that update, the actual file export feature on the live application completely breaks.
Oh, it shatters.
Because the system grabs my new logging text, runs it through map to lower, and suddenly it starts frantically trying to save user files with the expansion .pdf_document.
Exactly.
Which the operating system will definitely reject. The user loses their work, the app throws an error. And I would have absolutely no idea why my simple logging update caused a massive file-saving catastrophe.
And that right there is the blast radius of tight coupling. It's terrifying. You would be staring at the file export code, just scratching your head, because no one actually touched the get output path function.
I was just messing with the logs.
But the failure is completely silent until the exact moment the user tries to save their file. In enterprise systems, where you have millions of lines of code and hundreds of developers, These kinds of tightly coupled, string-based hidden dependencies are exactly why massive platforms sometimes suffer those mysterious cascading outages.
Wow. It really is the ultimate architectural sin.
Yeah.
The systems just don't have boundaries.
Yeah.
It's like having a company where, the sales team decides to change the font on their business cards, and somehow that causes the accounting software to instantly crash.
That's a perfect way to put it. You need shock absorbers between these departments.
Right.
And that concept of creating boundaries and shock absorbers is what Eng refers to as decoupling. Eng writes that the new approach, quote, decouples the internal show instance from our file system logic.
Letting the debugger just be a debugger.
Exactly. Let it do its job without the file system eavesdropping on its output.
Okay, so if the file system can't rely on the debugger's output, and it obviously shouldn't be blindly manipulating strings on the fly,
Yeah.
how does it actually know what extension to use?
Right. We need a real solution.
Which brings us to Eng's refactoring. And honestly, looking at the code in the journal, the solution almost feels surprisingly simple, like almost too simple.
The best engineering usually is. Eng introduces a brand new dedicated function called simply extension.
Okay.
There is no string manipulation, no asking the debugger. It is a pure translation function.
Yeah, the journal entry provides the exact mappings. It looks exactly like this. It says extension PDF equals, quote, PDF, end quote. Extension type equals type. Extension EPUB equals EPUB. Extension TXT equals TXT. And extension MD equals MD.
Notice how perfectly explicit that is. Eng highlights that these return strings are explicitly, quote, lowercased without leading dots.
So there is no guesswork anymore.
None. There is no map to lower command dynamically trying to squish capital letters at runtime. It is a hard-coded absolute truth.
It's almost like they hired a dedicated translator whose only job is knowing exactly which file extension goes with which format, rather than forcing the debugger to guess.
Exactly.
It's incredibly clean. But, I can see a skeptical developer looking at this and saying, wait, you just replaced a clever dynamic one-liner with a hard-coded list. That feels like a step backward into boring manual labor.
Yeah, people say that a lot. But boring is beautiful in software engineering because boring is predictable. By explicitly defining this mapping, Eng achieved two critical things that are mentioned in the journal. The code became type-safe and idiomatic.
Okay, let's really dig into the mechanics of that type safety, because that feels important. We know our listeners understand what basic data types are. But how does this specific hard-coded list leverage Haskell's compiler to create safety? Like, why is this functionally different than the old way?
It really comes down to a feature in Haskell called pattern matching, combined with the compiler's exhaustiveness checking.
Exhaustiveness checking.
Yeah.
Okay.
Yeah. The new extension function doesn't just accept any random piece of text. Its input is strictly locked to the export format type.
Meaning you literally cannot pass it a number or a random string or anything other than those 5 specific formats we talked about.
Right. It simply won't accept it.
Right.
And here's where the compiler's rigorous inspection comes back into play. Because the compiler knows that export format contains exactly 5 possibilities, it actively checks the extension function to make sure you have provided a mapping for all 5.
Oh, wow.
So if Eng were to add a new format tomorrow, say, they add CSV for spreadsheets, but they forgot to update the specific extension function, the Haskell compiler would throw a glaring error and just refuse to compile the program.
Oh, so it acts as an omnipresent spell checker. It basically forces you to handle every single edge case before the software is ever allowed to run.
Exactly. With the old map to lower string hack, the compiler couldn't help you at all. It couldn't verify if the output of the debugging log would actually make a valid file extension. It just let it run and hoped for the best. By mapping the types directly, Eng brought the risk back inside the factory. The compiler now absolutely guarantees that a missing file extension is mathematically impossible at runtime.
That is wild. It transforms the logic from, optical character recognition into mechanical linkage.
Yes.
The old way was taking a picture of a word, trying to read it, and guessing what to do. The new way is a physical gear fitting perfectly into another physical gear. If the teeth don't align, the machine just doesn't turn on.
That is the perfect way to describe the essence of type-safe design. And because the mapping is now explicitly defined in one single location, the final step, that getOutputPath function, is radically simplified.
Right.
The old fragile logic is entirely deleted. Eng replaces it with one clean command: replace extension path, extension FMT.
That's it. You just pass it the path and you pass it the result of the new translation function.
Yep, it completely eliminates the middleman.
Wow. It creates a single source of truth. And Ang writes that this centralization means if they ever need to add or update an extension in the future, quote, we only have one place to modify it.
Right.
And the best part is it doesn't break anything else. You can go back and change the debugging log to output a full paragraph of text if you want to.
Yeah?
The file system doesn't care anymore because it has its own dedicated translator. It is completely decoupled.
Which brings us to the second word Ang used to describe the final code, idiomatic.
Idiomatic.
Yeah. Idiomatic code means you are writing in a way that feels natural to the specific programming language you're using. You aren't fighting the grain of the wood, you are working with it.
Because every language has its own idioms,
Yeah.
right? Its own natural rhythms.
Exactly. And Haskell is a language built around strong types and explicit data transformations. Trying to sneak around the type system by manipulating strings on the fly is highly idiomatic in Haskell. It's like trying to speak French by rigidly applying English grammar rules. I mean, you might eventually be understood, but it's clunky, it's confusing, and it's prone to severe misinterpretations.
But by using pattern matching and explicit types, Ang is speaking Haskell's native tongue.
Exactly. And because of that, the code becomes self-documenting. As Ang noted, it is now, quote, immediately clear which file extension corresponds to which format.
You don't have to guess?
No, you don't have to hold a complex mental model of how map to lower interacts with the show instance in your head. You just read the list. It takes zero cognitive load to understand what the code is doing.
Let's synthesize this journey for you, the listener.
Yep.
Because we started with a system that was fundamentally anxious and brittle. It relied on a clever but deeply flawed hack hijacking, a diagnostic debugging tool, and using string manipulation to just guess a file extension on the fly.
Yeah.
It was basically a ticking time bomb of tight coupling, where a simple update to a log file could trigger a catastrophic failure in the user's ability to save their work.
And we saw how string manipulation pushes all the risk away from the safety of the compiler and out into the live runtime environment, resulting in those silent, unpredictable errors.
But then we followed Ang's refactoring. And the solution wasn't to write a more complex string parser. The solution was to throw the string manipulation out entirely.
Right, get rid of it.
By decoupling the systems and introducing a dedicated hard-coded extension function, Ang leveraged Haskell's pattern matching to create mechanical linkage. The code became type-safe, preventing edge cases from ever compiling, and idiomatic, making it instantly readable.
And the profound takeaway here really extends far beyond Haskell syntax. It is a fundamental philosophy of how to build things that last.
Yeah.
Whether you are managing a team's workflow, setting up a database, or just organizing your own digital life, do not reuse diagnostic tools for operational logic.
Build boundaries. If a system requires a specific translation to do its job, build a dedicated mechanism for that translation. Don't rely on eavesdropping or invisible dependencies. Design your systems so that a change in one room doesn't silently knock over the furniture in another.
It requires abandoning the temptation of the clever shortcut. I mean, taking the time to explicitly map out relationships might feel tedious in the moment, but that predictability is what actually scales.
Right.
That explicit clarity is what allows a massive system to grow without collapsing under its own weight.
It's the difference between hoping something works because it didn't break today and knowing it works because the architecture fundamentally guarantees it.
Absolutely. And if we look around at the digital world we rely on every single day, our banking portals, our power grid management systems, the communication networks keeping our phones active, we really have to wonder about the underlying architecture.
Yeah, it makes you think.
How much of that critical infrastructure was built on tight deadlines, using those clever shortcuts? How much of it is secretly just a massive, tangled web of string manipulation, silently waiting to snap the moment an innocent developer decides to capitalize a single letter in a log file?
Wow, that is a staggering thought to consider the next time a critical application crashes for seemingly no reason at all. Thank you for joining us on this deep dive. Take a look at the systems you interact with today and ask yourself if you're relying on mechanical linkage or just reading the check engine light. We'll see you next time.